All right, last time I started out telling you about some of the properties that chemists had discovered that allowed them to start to see relationships between the various elements and see that the chemical elements that had been discovered sort of naturally fell into certain groups that had these similar properties. Now, the guy who did the crucial work here is a Russian chemistry teacher, Dmitry Mendeleev, and he published the first version of what is now called the periodic table in 1869. And by the time Mendeleev came along and started doing his work in the 1860s, chemists had discovered a lot of elements by this point. I think I told you how many, remember the Greeks thought there were how many? Try 4, right? You know, earth, air, water, fire. But, I mean, Lavoisier, of course, came along and changed all that and showed how to objectively distinguish between elements and compounds. But in Lavoisier's day, only about, does anybody remember how many elements I told you Lavoisier knew about? No, he knew more than that. There were 7 metals, that's probably why 7 came to mind, that people knew about from the, had known about for a long time. But the total number of elements, when you add in all the gases and the various other things people knew, came to, I think in Lavoisier's day, he knew like 21. Now, by the middle, well, let me give you another quiz. When did Lavoisier live? Troy.
18th century.
Yeah, you got the century right. Okay, so we got it narrowed down to a century. Anybody can narrow it down further? How did he die? French Revolution. When was the French Revolution?
1789 to 1793.
Exactly. Okay, so that's actually, Evan said 1789 to 1793. So the Lavoisier's major book came out in 1789. So it's at the end of the 18th century. So it's 80 years before Mendeleev publishes his first crucial paper on the periodic table. Now, like I said, Lavoisier knew about 21 different elements, okay, that couldn't be broken down further. So he had established that these were elements. By the middle of the 19th century, chemists had basically discovered all of the elements that were easy to discover, that existed in any significant quantity. And then a few more besides that I'll tell you about. They started discovering, in the 1860s, they started discovering even elements that existed only in trace quantities by new techniques. So the bottom line was, by the time Mendeleev publishes his paper, he knows about 62 elements. Okay, so now things are starting to get complicated. I mean, 62 is a lot to hold in mind. And it's important to start seeing the similarities between them and putting them into groups. And starting to see patterns and recognize how to make sense out of this enormous complexity of 62 elements. Okay, so that's what Mendeleev starts to do. Now, I told you last time that he's using some basic properties of the elements to see these similarities. He's using some basic properties that had been discovered just in recent decades. Well, first their electrical properties, okay, that Lavoisier obviously didn't know anything about because electrolysis hadn't even been invented yet. But in the 19th century, chemists had been stimulating chemical reactions using electricity and seeing which electrode the chemicals would go to and so on. And so they had associated with the elements their electrical properties, whether they, when they got into solution and they became ions, whether they tended to become positive or negative. Okay, then the other major property that they had discovered was valence, right. And they had figured out that, you know, if you think in terms of atoms, then you can associate with each of these atoms I mean, I've been calling it a number of hooks, you know, where they can attach to other atoms. Now, atoms aren't literally like Christmas tree ornaments. They don't have hooks, but they probably don't even have little pieces of Velcro attached to them. But they have something that enables them. There's something in the structure of, say, a carbon atom that it can attach to as many as four other atoms, 4 hydrogen atoms, for instance. There's something in the structure of a hydrogen atom that limits it to attaching to one other atom. So they had noticed these differences. So putting together these properties of the electropositiveness or negativeness of the atoms and the valence, Mendeleev came up with these groups. And so let me just, I think I started to actually tell you about some of the groups. Let's first consider the valence 1 electropositive group. And what the various elements in this group so hydrogen, lithium, sodium, potassium, and a recently discovered element, rubidium. Throw that one in there too. And the reason I've listed them actually in this order is the other key property that Mendeleev recognized that had to be taken into account, you know, when you start to trying to see these patterns among the elements, is their weight. And hydrogen, of course, is the, let me switch to green here. Hydrogen is the lightest element, 1. Lithium is 7 times heavier than hydrogen. Sodium is 23 times heavier, potassium 39, and rubidium is 85. Okay, so I've listed them in ascending order of heaviness here, weight. Let's just. Okay, now let's, and like I say, all these elements are highly reactive, and they'll, and they all have, valence 1. Basically, they have one hook to bond to another atom. Now, there's another group. Let's just look at the other valence 1 group, but which is electronegative. Okay, so it also, the most famous element in this group is chlorine. At this point, that have been known about for, over 50 years, and extensively studied by chemists. But there were a bunch of other elements that reacted very similarly with chlorine that were known at this time. There's fluorine, then there's chlorine, and then bromine and iodine. It's just I, actually, but I just started feeling guilty about abbreviating everything. All right, so fluorine is 19 in atomic weight. Chlorine is 35. Bromine is 80. And iodine is 127. Okay, so again, you see this ascending pattern of weights here. And again, you see elements that react very, very similarly. They'll all combine one-on-one with hydrogen and form acids. So they chemically they react the same. So they naturally fall into these groups. Now, let's. Now you might think, some chemists did think, when Mendeleev started playing around with putting these elements into groups like this, that that's nice to see these similarities, but where does it really get you in chemistry? Is it going to give us any new knowledge simply by putting elements into groups like this? Well, turned out that it did, and I want to give you examples of a couple of groups here that Mendeleev put together and noticed something peculiar about, and then he was able to make some predictions. So let's go to the next group now that you've sort of got the pattern of what he's doing here. Okay, consider this group. Valence 3 electropositive. Now, what the elements that were known in this group that Mendeleev knew about were boron, okay, that's B, and its weight is 11. Then aluminum, and its weight is 27. And then The next one that Mendeleev knew about was an element called indium, In, and its weight is 115. Now, does anything strike you as strange about that group, Troy?
How from the aluminum to indium jumps a lot more than the other groups?
Yeah, there's a big jump here in weight, right? From 27 to 115. And there's no known, I mean, based on the other patterns of some of the other groups that Mendeleev had already looked at, you would expect to find something in here in between before you got to 115, right? And that's exactly what Mendeleev thought when he looked at this group. He thought, well, there seems to be something missing here. And it should be, you know, roughly halfway in between these other two atomic weights. So he started looking at the elements that were known to be around, say, atomic weight 70. And he noticed that, for instance, let me see, I think one element that was known was zinc has an atomic weight around 65. But it doesn't have quite the right valence. Okay, so he predicted, Mendeleev decided, just looking at these patterns, well, there must be an element out there that does have valence 3, slightly electropositive, and has an atomic weight of, you know, around 70. He actually predicted 68. Okay, so Mendeleev, based on this hole he sees in his table, makes a prediction. And he predicts he goes out on a limb here, and he says that if chemists look hard enough, they will find a new element that is chemically somewhat similar to aluminum, but heavier, quite a bit heavier. And he predicts that the atomic weight will be 68. It will be a metal. He even predicts the density of the metal, 6 grams per cubic centimeter. He says it's going to have a low melting point based on the patterns of the properties of these elements of which it is a group. He says that it will react with oxygen, whatever this new metal is, that it will react with oxygen and combine 2 atoms of this new element to 3 oxygens. Okay? So he's even telling us how it will react, what its oxide will be. And he even says things like how it will dissolve in acid. You know, he says it won't be highly reactive with acid, but it'll dissolve somewhat. Well, and he even goes so far as to tell other chemists how to find it. There's this new method for determining elements called spectroscopy that I'm going to tell you about later. And he says that's how to go look for it. A few years later, in 1875, chemists discover a new element. It has atomic weight 70. It's a metal. Has a density of 6 grams per cubic centimeter. It has a low melting point of 30 degrees centigrade. And it forms a exactly this oxide. Dissolves slowly in acid, and and they discovered it with this new technique, spectroscopy. Troy.
Is its abbreviation actually X, or are you just...
No, it's just an unknown right now. I'm going to replace the X now. They decided to call this gallium. And its abbreviation is just GA. So if you want, you can get rid of the X's and fill them in with gallium now. But that's very impressive. I mean, if you these, just in a sense, starting out just playing this pattern recognition game, trying to fit the chemical elements into these groups that show fundamental similarities, then noticing a hole in one of his groups, he's able to predict, there's an element out there nobody's found, and actually even predict a lot of its properties, and then chemists go out and find it. So that definitely shows he's on the right track, right, Ben?
So, by low melting point, do you mean that it melts really fast? Or?
Yeah, it melts easy at a pretty low temperature. I mean, this is really just 10 degrees above room temperature.
What would it be called, like, if it melts really, like, it takes a long time for it to melt?
Well, it's, I mean, there's a lot of metals that won't melt until extremely high temperatures. I mean, take tungsten that is used in light bulbs. I mean, the reason it's used in light bulbs is because you can heat it up to incredibly high temperatures and it still won't melt. You can heat it up to, 3,000 degrees or something for its melting point. So, I mean, tungsten would be 3,000 here. Gallium is, 30. So it's there's a really wide range of temperatures that are required to melt things. I mean, this is a metal, but it only exists in trace quantities. You can't get. I mean, you don't see big chunks of gallium. Usually, gallium is found in little trace elements in zinc and that kind of thing. So, yeah.
What's used for making, like, spaceships and stuff?
Often titanium, tungsten. So really tough metals that that have very high melting points. You know, if you had a spaceship that was made of gallium, it wouldn't do very well, because as soon as it started going into the atmosphere, the whole thing would melt, right? Okay. Now, this wasn't the only hole in his table that Mendeleev identified. Let me give you one more. This is actually why chemists took Mendeleev's table seriously. You know, at first, when his paper came out, it didn't create a big stir with chemists. Oh, okay, so he thinks he's found these patterns, big deal. But he made these predictions, and then people actually went out and found the elements, and then they really had to take Mendeleev seriously. All right, so I'm going to give you, I'll give you one more here. All right, let's look at the carbon group. Now, carbon, as we know, is valence 4, and it's not electropositive or electronegative. So let's just call it neutral.
How is it neither?
What that means is it can bond with things that are electropositive or things that are electronegative pretty much equally, and doesn't lean one way or the other itself. Yeah.
So, is it possible to do electrolysis on carbon dioxide, or do you?
Yeah, I suspect it would be. What would the electrode the carbon goes to, though, depends on what it's bonded to. So, for instance, in that case, if it's bonded to oxygen, well, oxygen is strongly electronegative. So in that case, the carbon would act electropositive. But if you put it with something that was electropositive, then it would act electronegative. So that's why I say it's neutral in that regard. Now, there were a few elements in this group that were known. Like I say, carbon, which is sensibly abbreviated C, and it has a weight of 12. And then there's another very abundant element, silicon, that has weight 28, Si. Also pretty sensible. Then they also knew about tin, which is very logically abbreviated Sn. And tin is 119. So again, you see this big gap between silicon and tin. And Mendeleev looked at that and said, well, okay, we should look for another element that falls in between here that has, again, atomic weight, maybe a little over 70, and and has properties that are commensurable with the other members of this group. So he looked at this group and the surrounding elements that were, that weighed a little more than 70, and came up with predictions for what this missing element would be like. And again, he did shockingly well. So let me make two columns here. Mendeleev's prediction, and then what was actually discovered. Now this actually wasn't, this element I'm going to tell you about now wasn't discovered until 1886. But it's,
Mendeleev alive at that time?
yes, I believe he was. Yeah, I think he lived into the 1890s. So he predicted here. By the way, I'll just go ahead and rather than call it X this time, I'll tell you what they called. It must have been discovered in Germany because it's called germanium. And the symbol is GE. Now, Mendeleev predicted an atomic weight of 72. And turns out it's 73. He predicted a density of 5.5 grams per cubic centimeter, and it turns out to be 5.4. He said it would be a gray metal, and it is. He said it would combine with oxygen, 1 atom of germanium to 2 atoms of oxygen, and it does. He said it would react with chlorine, 1 atom of germanium to 4 atoms of chlorine, and it does. He let me see. He said that this would be a volatile liquid with a low boiling point, below 100 degrees. And it is. It turns out that when they actually discovered germanium and were able to react it with chlorine and form this liquid, the boiling point was like 83 degrees. And Mendeleev had said below 100. He did remarkably well here. It's like the guy is psychic, huh? So, I mean, all this by way of, I'm not going to drag you through the whole periodic table now. Like I said, Mendeleev knew about 62 elements at this time. And so he had a whole bunch of these groups. Yeah, Troy.
Did most groups just have 4 and the first one that we did have 5 or now?
Oh, no, actually most of the groups actually have more members than I've even told you about, some of them. I mean, if you look at the periodic table, it's these vertical groups that I'm telling you about. I mean, for instance, even the first one I told you about, the lithium, sodium, potassium group, I went up to rubidium. Below that, there's even cesium, which is even heavier, and then there's even one other element after that. Some of the heavy elements weren't discovered until later, and so I haven't bothered to tell you about them. One thing you have to, one thing I should tell you about these elements is, 90% of the stuff around us is basically made of the same stuff. I mean, if you look at carbon, hydrogen, oxygen, nitrogen, and then a few of the main metals, the 7 major metals that have been discovered, back in the ancient world, that makes up probably 98% of the mass of everything around us. Now, they've discovered lots of dozens of other elements now, but they exist in relatively small amounts. Yes?
What is plastic made of?
Oh, plastic is, again, mostly carbon and oxygen, right? What is, and hydrogen, right? Yeah, it's a hydrocarbon. So it's made up of the same stuff that, yeah, I mean, it's a combination of, what this explosive light gas that you've seen, hydrogen, and, pencil lead. But you can get lots of different materials out of various combinations of those things. Okay, but of course now I don't mean to minimize the importance of these elements that exist in small quantities, because people have found remarkable uses for these things. I mean, gallium is even used in certain kinds of semiconductors, so it makes it into things like computers. And so, I mean, you don't have to necessarily have a lot of a material in order to make good use out of it. Okay. I think I'm going to leave it for a future chemistry class of yours to go into a more in-depth study of the periodic table. But my main point here, I mean, my main goal here is to first show you how scientists came to know that everything is made of atoms, and then start discovering the properties of those atoms, and then the discoveries that enabled them to make that they never could have made otherwise. So in that connection, if you look at what Mendeleev did, notice how he used this concept of valence. Now, the whole idea of valence depends on the atomic theory, right? It's thinking in terms of atoms, and then seeing that you can ascribe this property to atoms, that they have, in effect, a certain number of hooks to bond with, to attach to other atoms. And using that idea, that enables him to organize all these elements in similar groups, and then that leads him to the discovery of new elements. Now, I showed you 2 new elements that Mendeleev predicted that were later discovered. He actually made a total of 6 predictions, and he was right in all 6 cases. So now one other thing, I'll tell you a little bit more about this afternoon, but I'll mention it now. I mentioned there was a new technique for discovering these elements that Mendeleev recommended that chemists use to find the small amounts of these new elements that he was predicting. And the technique is called spectroscopy. Now, what that is, what had been discovered is that each element emits light that is like its own little signature, that comes from certain kinds of light that come uniquely from that element, that you don't get from other elements. Now, we've already seen that. So I'm actually switching topics here, so I should write a new topic up on the board. Remember, we talked about Thomas Young's experiment where he discovered that light was a wave, right? And then we talked about the whole electromagnetic wave spectrum when I covered Maxwell. So light consists of this this whole spectrum of different wavelengths that, for instance, let's do it this way. Light wavelength. I'll just remind you, red light is the far end of the visible spectrum. The long wavelength end is, well, let me start with do it in order. Start with the short wavelengths. So we have violet, blue, green, yellow, orange, red, say. And all of these different colors differ in their the length of the waves of these light waves. And down at the violet end, you start at about 430 nanometers. Up at the red end, you go to 690. And then in between, you have the various various numbers in between. So I think, let me see, yellow, I think you've gotten to, say, about 570. So scientists knew, of course, about this whole spectrum and about the fact that that wavelengths could be associated with the light here. Now, when it was around the 1850s when they first, a physicist named Kirchhoff noticed that if you heated a material up, let's say you took sodium, heated it up super hot, okay, and it started glowing like crazy. You started getting light from it. Well, you didn't just get all colors of light. You got specific wavelengths of light. For instance, sodium emits really, really strongly in the yellow. I mean, you would have a really sharp line right around 570 nanometers. A whole bunch of light right at that wavelength, and then nothing at other wavelengths. And that's characteristic of sodium. Okay, so once you know that, then if you heat a material up, I mean, let's say you don't know what salt's made out of. Okay, you heat it up, super hot, and and then you collect the light that you get from it and put it through this instrument that allows you to determine its wavelength. Okay? And you, lo and behold, it comes out at 570 nanometers. Well, that's the signature for sodium. Okay? So if you can start, this gave physicists and chemists the idea of, well, now we've discovered this connection between light emitted by elements and what the element is. So we can now start analyzing the chemicals that are in something that is emitting light just by looking at the wavelengths of the light. So I'm going to tell you, I'll tell you more about that this afternoon. That's how all these trace elements were discovered. After they had discovered all of the easy, abundant elements, the little trace elements were discovered with spectroscopy.